So this is our third lecture on the anomalous Zeeman effect. So just to remind you, when we did the Zeeman effect, the normal Zeeman effect was when we had it in a strong magnetic field and we saw all those equally spaced spectral lines. But we said there's an even more common Zeeman effect called the anomalous Zeeman effect. And again, what we had said is that the electron, even though the electron, from the electron's perspective, the proton is going around him. So there is always a magnetic field on that electron. And we calculated that magnetic field the last time right here. And that magnetic field, we can put it in terms of the angular momentum. We want to put it in terms of stuff we can measure. We also said that the magnetic dipole moment was given by this, where G sub s, at least Dirac calculated to be 2, exactly 2. And remember, our Bohr magnetron is EH bar over 2me. So when we calculated the energy of this magnetic dipole in a magnetic field, you remember it was just minus mu dot B. And so when I dot these two, it just came out to be this right here. And the only thing is, this is from the perspective of the electron. Now, remember, it's really the electron going around the proton. So when I do a coordinate shift, a Lorentz coordinate shift from the electron's perspective back to the proton's perspective, it actually just brings in a factor of 2 in the denominator right here. So it's 1/2 as much. Okay, and you noticed what we get here is the coupling between the spin of the electron and the orbital motion of the electron. They call that spin orbital coupling. So before we had spin orbital coupling, we had, if we had a magnetic field here, we had the S going around, and S was a good constant, and the S sub z was a good constant. L was a constant, and LZ was a constant, and so our good quantum numbers were NL, M sub L, which remember is related to the Z component of this, and M sub S, which is related to the Z component of that. But with spin orbital coupling, you have L plus S now is a total angular momentum, which we call J, which is the sum of the two angular momentums. And L is just going around and S is going around, but they're not good quantum numbers, they're not fixed. But J sub Z is this Z component of the total angular momentum. So they're both orbiting J, but J is going around like this. So J is now a good value, which is fixed, and J sub Z is fixed. So now our good quantum numbers are NL, little j, and M sub J, where M sub J goes from minus J all the way up to J in steps of 1, and our range of J is, if L is equal to 0, then J can only be 1/2, and if L is not equal to 0, then J can be L plus or minus 1/2 only. Okay, so that's our range of what J can be, and our spectroscopic notation was usually NL sub J. Okay, so when we calculated all this right here, when we calculated this change in energy, remember we used this perturbation theory, and we ended up with our change in energy was given by this right here. So this is the shift in the energy. And you'll notice it depends on the old Bohr energies, but there's an alpha squared in there. Remember, alpha is 1 over 137. So this is 1 over 137 squared. All of these, rest of these, are pretty close to just 1 or 2. You know, these are all, but this is 1 over 137. So that's why this effect is like 10,000 times smaller than the Bohr levels right here. Okay, but this isn't the end of the story, because there is another effect that's on the same size as this. And if I correct for this spin orbital coupling, I have to correct for this other effect right here. And this other effect is because of our definition of kinetic energy. Remember, we're using the kinetic energy as P squared over 2m. But that's only good classically. When you start to go really fast, relativistically, the kinetic energy changes right here. And we said, well, it's a very small effect because even for the hydrogen atom, when we're in the lowest orbit, remember the electron was moving about 1/100th of the speed of light. But 1/100th of the speed of light makes about this same size of effect. So I need to take into account a better approximate value for the kinetic energy. You remember, relativistically, the kinetic energy is, what is it? It's the total energy minus mc squared. I don't want to bring in the one with the velocity. And we know what the total energy was. That was the square root of p squared c squared plus m squared c to the fourth minus mc squared. So that would be an exact for the kinetic energy, but I don't want it to be quite as exact. What I'd like to do is I'm going to pull out an mc squared out of here. So you got k is equal to mc squared. This term, if I pull out an mc squared, just becomes 1. So I'm going to write that term first. So that's 1. And then this is plus p squared c squared over m squared c to the fourth. So I just pulled out the mc squared. And then we have minus mc squared, but since I factored it out, it's just minus 1. Okay, now this is a small term right here. So if we look at something like the square root of 1 plus x, where x is small, and just put it in a series right here, this is just 1 plus x over 2 minus x squared over 8 plus dot, 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 dot. Okay, so we have kinetic energy equals mc squared. So my x is everything in here. So it's just 1 plus a half of this, which is p squared c squared all over 2m squared c to the fourth. Then we've got minus 1/8 of that squared. So it'd be 1/8 of all of this p squared c squared all over m squared c to the fourth squared. I'm only going to go that far right there. The next term would be this cubed right here, but this is getting smaller and smaller effect, so I'm only going to take it that far. And then minus 1. So this would be a better approximation than just this right here. Now you'll notice the 1's dropped out. And now if I just multiply this back through, we get k is equal to. Well, when I multiply this times this right here, the c to the fourth over c to the fourth, that's gone. We get p squared all over 2, and then you've got m and an m squared, so that's 2m. And then we have minus, we got p to the fourth, c to the fourth, p to the fourth, c to the fourth. Well, we're going to get c to the fourth over c to the eighth. Well, we'll just write it all in. C to the fourth all over 8m to the fourth c to the eighth. Which is, and then I can simplify this term right here. This is p squared all over 2m minus p to the fourth all over 8 m to the fourth, there's an m to the fourth and an m here, so that should have just been m cubed. And we had c to the squared, and then that's c to the fourth, so that's c to the sixth, over c to the eighth. So that was really just c squared right there. Okay, and so that's 8m c to the, actually just remember that was c to the sixth in the top and c to the eighth in the bottom, so it was c squared down here. mc squared. Okay, so you'll notice what we had before was this right here. So now all we'd have to do is, we just need to say, well, there's a slight correction in there, which is this. So if we want to say, what's the correction for the energy just due to that term, the change in energy, what do? We just put our psi, we put our correcting term in there, which is just that, minus p to the fourth, I guess it's the operator, all over 8mc squared, psi. And that would be the correction due to our incorrect kinetic energy using the classical, right? This would be the first correction. If we wanted to get it totally correct, we would take all the terms, but this is enough terms. The next term is just too small to matter right here. Okay, so this is what we want to calculate, and hopefully we can then combine it with this one right here. So what do we have? We have delta E equals, I'm going to pull out the minus 1 over 8mc squared, and then we just get psi p to the psi. And then I think what I'm going to write, instead of p to the fourth, I think I'll write it as p squared times p squared. P squared times p squared psi right here. Okay. But you remember we do know what p squared over 2m is acting on psi plus u times psi equals E psi. We do know that's true. That's just Schrodinger's equation right here. So I could calculate what p squared is on psi right from here. So I'm going to move that to this side. So it's E sub n minus u. So we got p squared acting on psi is equal to, and on this side, I'm going to have an E sub n minus u acting on psi, and then we multiplied everything by 2m. Okay, so now what I'm going to do is, if I did this right there, that would give me this times psi, because that's what we have right there. And then when I act on it again, it would just be this squared times psi. So this thing is just going to give me psi, and then it's just going to give me this part squared, because every time I act on it, it gives me this, and then I act on p squared again, it doesn't do anything to this, and it just gives me another one of these. So we just have 2m E sub n minus u, and everything in here is squared, because we do each p squared is going to give me another one times psi. Okay, well, this right here, if I squared it out, first of all, the 4m squared can come out in front. That's 4m squared. And then, what are we going to have? We're going to have psi, and then we just square that out. The first term squared is E sub n squared the middle term is minus 2e sub n u plus the last term squared plus u squared acting on psi. Okay, remember we do know what u is. I don't want to plug it in quite yet, but u we know is just the potential between the proton and the electron. The potential right there was just our minus e squared all over 4 pi epsilon naught r. Okay. Well, so let's just distribute this thing through. So this, remember what we're calculating here is my delta E. That's going to equal to 4m squared except we also have, don't forget, we also have this out in front, so there's also a minus 1 over 8 pi 8m c squared minus all over 8m c squared. Okay, and now we have to bring this like that. We're going to have psi with just the e sub n squared psi. We'll just distribute it through. So we got psi e sub n squared psi minus 2, well, let's just write it like this, psi 2 ENU psi plus u squared psi plus psi u squared psi. Right there. Okay, well, this can come out in front. It's a constant right here. It can be pulled out in front, and we're just left with psi, which is 1. So this term right here is just e sub n squared. The 2en can be brought out in front. U isn't a constant. Remember, it depends on r right there. So I can't, so this is minus, I'll bring out the 2e sub n, and we've got psi u psi. And then the last term is just plus. We'll leave it the same, psi u squared psi. Okay, so that's what everything inside of there would be. Now, u, we might as well plug in what u is here. So we've got delta E is equal to, I'll cancel a 4 here, and cancel an m, so that's minus m all over 2 c squared and so we've got e sub n squared minus 2en. And then the u is this. I can pull out everything but the 1 over r in there. And so it'd just be minus e squared over 4 pi epsilon naught, which means this is a plus e squared all over 4 pi epsilon naught. And then what do we end up with? We end up with psi 1 over r psi. Well, that's just the expectation value of 1 over r. Remember, that's just the expectation value. And then we got plus u squared. Well, if I square this, it's back positive, and it becomes it'd be e squared over 4 pi epsilon naught squared. E squared all over 4 pi epsilon naught. And it's all of that squared. And then we would have this would be a 1 over r squared. It'd be the expectation. You're just left with a 1 over r squared there. So it's just 1 over r squared. Okay, so let me just see right here. I just wanted to just check what we had right here. And 4m squared. 4m squared all over 8m. One thing here. This was m cubed right here. So that was still m cubed right there. Just wanted to. So this was still m cubed. So there's two more factors of m here. So that should have been m cubed, which leaves you with just one m in the denominator, not in the top. So that's just 1, and that's m right there. Okay. All right. So now we just need to calculate what this is and what that is. We calculated this already for the hydrogen atom, but we did it for the lowest state. If you remember what we got for the lowest state, it was just 1 over a naught right here. That was for n equal to 1. But what about when n equals 2 and n equals 3? For any n value, well, then all it does is it just adds an extra value of n. I don't want to work it out and just show, but we did it for the n equal 1 case, and it was just 1 over a naught right here. Now, we could have done the 1 over r squared, and 1 over r squared, we didn't do that, but we could have right there, and this ends up being 1 all over L plus a half n cubed a naught squared. Okay, where again, a naught was the Bohr radius. Remember, I should write down what that Bohr radius was. That a naught was equal to 4 pi epsilon naught h bar squared all over m e squared. The other constant I should probably bring up is E sub n. Remember, E sub n was our Bohr energies, which was the minus 13.6, but I don't want to use the 13.6 right here. It's actually minus m e to the fourth all over 2 times 4 pi epsilon naught squared h bar squared n squared. So those were our Bohr energies. And one last one was our fine structure constant. Alpha is equal to E squared all over 4 pi epsilon naught h bar c. The reason why I want the alpha is because I want to get this energy shift kind of in this same format with an E sub n alpha squared over an n squared out in front. That way I can add them up a little bit easier right here. So if we plug in this up into here and plug that into there, then we can get the change in energy right here. The delta E is equal to minus 1 all over 2 mc squared. You'll notice this has units of energy, but these all have units of energy squared. You notice there's an energy squared. So you're left with an energy. And we're left with E sub n squared. Well, okay, we'll do it in the next step. E n squared plus 2 E n E squared all over 4 pi epsilon naught 1 over r, which is this, 1 over n a naught, plus e to the fourth all over 4 pi epsilon naught squared times 1 over r squared, which is this term, 1 all over L plus a half n cubed a naught squared. N cubed a naught squared. Close off. Okay, so now I just want to simplify this so that it looks similar to this right here. So what I'd like to do is out of each of those terms, each of these terms, I'd like to pull out an e sub n alpha squared over an n squared. That way I'm comparing them a little easier. So let's look at each term individually. So looking at this first term right here, this first term, we got minus en squared all over 2mc squared, 2mc squared. Okay, and so what I want to do is I want to write this as e sub n. I want to pull out an e sub n. So we'll pull out one of the e sub n's. So we got an e sub n on the other side. I would like to put an alpha squared here, alpha squared, which means I need an alpha squared there. I have a minus there. There's a minus there. I want an n squared down below, n squared, so I'll put an n squared up above. And then I still have the 2mc squared, 2mc squared. So I just want to calculate this because I already factored out that part right there. Okay, so this thing is e sub n alpha squared all over n. Okay, now we've got minus e sub n. Now I'll plug in because I don't plug in this. Minus that would make this a plus. So we just got me to the fourth. Me to the fourth all over 2. 4 pi epsilon naught squared. 4 pi epsilon naught squared. H bar squared n squared. H bar squared n squared. Okay, that took care of this. Times n squared. Down below we have 2mc squared. And then we have an alpha squared in the denominator. So that means we have this squared in the denominator. So you got an e to the fourth. Bring it up. We got this squared. 4 pi epsilon naught squared. H bar squared c squared. Okay, now let me see if I can cancel any terms here. Well, there's a 4 pi epsilon naught squared. I can cancel with that 4 pi epsilon naught squared. We get an e to the fourth. We get an e to the fourth. We get a c squared. We get a c squared. We got an h bar squared. We get an h bar squared. We get an n squared and an n squared, an m and an m. Oh, so it looks like the only thing that's left is 1/4. So this first term is e sub n alpha squared all over n squared. Sorry, there was an n squared there. N squared times, and this is just 1/4. Okay, so I've handled the first term right there. Now I want to handle the next term right here. So let me box this in. There's the first term. Now the second term is a minus 2 e sub n. So we got minus 2 e sub n e squared all over 2mc squared c squared. And then we still have the 4 pi epsilon naught n a naught. 4 pi epsilon naught n a naught. Okay, so what did we want to do? I'll do the same thing what I did with before. I'll factor out the e sub n. But I only have one, so I won't have another one inside. And I need an alpha squared here, because I want it to look like this. So I'll put an alpha squared down below. I want an n squared here. So I'll put an n squared there. And then I'll put the rest of this stuff in here. I got the minus 2e squared. Minus 2e squared. All over 2mc squared. 2mc squared. C squared. Times 4 pi epsilon naught. Times n a naught. Okay, now I just have to simplify that. I better plug in what alpha and what a naught is, and so things will hopefully cancel. So this is e sub n alpha squared over n squared. Okay, and then we're left with minus 2e squared n squared. Minus 2e squared n squared all over. I'll put the alpha, well, okay, if I put the alpha squared in there, that's going to be down in the bottom. So we got e to the 4th all over 4 pi epsilon naught squared h bar squared c squared. 4 pi epsilon naught squared h bar squared c squared. Okay, that took care of the alpha squared. Then we still have the 2mc squared. 2mc squared, another 4 pi epsilon naught, n a naught. A naught was right here, but we're in the denominator, so we'll flip it right here since it's in the denominator. So we got an m e to the me squared all over 4 pi epsilon naught h bar squared. Epsilon naught h bar squared. Okay, so hopefully some stuff in there will cancel. Well, let me see. We got the 4 pi epsilon naught squared, and we got the 4 pi epsilon naught squared down below, so that cancels with that. We have an m here. That cancels with that m. We have a c squared, cancels with this c squared. We got a e squared, that's e to the 4th over e to the 4th. That's all gone. We got an h bar squared and an h bar squared. We have an n squared and an n. So that means it just gets rid of one of the n's. I just wanted to make sure we only have one n. Okay, and just this last n I noticed is when I wrote out this 1 over r, I forgot this is a naught n squared, which just made this n squared, which just made this one right here n squared. So all of the n's canceled right here. There wasn't any n left right here. And so this whole thing just came out to be e sub n alpha squared all over n squared, and the only thing left we have is minus 1. Okay, so it's easy for me to add these guys up, and then we just have the one last term, which is this term right here. So we have minus 1 over, the last term is minus 1 over 2mc squared. And then we have times this over here. So it's e to the 4th all over 4 pi epsilon naught squared times L plus a half times n cubed a naught squared. Okay, so that term I want to write like this, like these ones right here. So I'm going to pull out, I need to pull out an E sub n. I don't have an E sub n in there, so I'm going to have a 1 over E sub n inside. I have an alpha squared, which means I need an alpha squared there. And I have an n squared here, and so I need an n squared there, and then I just need to put everything else up there, which is the minus e to the fourth, and then down below here we've got a 2mc squared, 4 pi epsilon naught squared. L plus a half, n cubed a naught squared. Okay, and hopefully all that stuff cancels out too, right here. So we end up with E sub n alpha squared all over n squared. Now, there's a minus here, but E sub n also has a minus in it. We have it right there. So there's no minus, so we can get rid of the minus. So we have an n squared e to the fourth all over E sub n. Well, we already took care of the minus sign, so it's m e to the fourth. M e to the fourth. And on the top, it gives me 4 pi epsilon naught squared h bar squared n squared. So that takes care of this. Then we have an alpha squared in the bottom, which is this. That's e to the fourth all over, then this 4 pi epsilon naught squared, 4 pi epsilon naught squared, h bar squared c squared. Okay, so that takes care of that. Then we had the 2mc squared, 4 pi epsilon naught squared, L plus a half, n cubed, a naught squared. Well, a naught squared, and that's in the denominator, so we flip that, so it's m squared e to the fourth, m squared e to the fourth, all over 4 pi epsilon naught squared, h bar to the fourth. Okay, so hopefully a lot of stuff here will cancel out. Well, let me see. We've got, if we look at all the h bars, there's an h bar squared, h bar squared, h bar to the fourth. So they're gone. We got a c squared, they're gone. We got a 4 pi epsilon naught squared, 4 pi epsilon naught squared, 4 pi epsilon naught, and 4 pi epsilon naught squared. They're all gone. We've got an m squared and an m and an m. They're gone. We've got an e to the fourth, e to the fourth, e to the fourth, e to the fourth. They're all gone. We've got the 2's are gone. We've got n squared, another n squared, that's n to the fourth over n cubed, just one n in the numerator. So there's just going to be an, this is gone, and that's gone, and that's gone. And I think, so we end up with e sub n alpha squared all over n squared. And I'm left with just an N over an L plus a half. Okay, so now I can add these to get the sum, this delta E. I'll add up these three pieces that we just did. So this delta E, again, this is the correction due to the kinetic energy. It gives me E sub n alpha squared all over n squared. And then we just add these up. We've got a fourth and we've got a minus 1. That's minus 3/4 plus n all over L plus 1/2. Okay, so there is the, you notice it's on the same order. It's this is a unit, that's around 1 or 2 or 3, somewhere in that range. And you've got this factor here. Same with what we had on the other side for the spin orbital coupling. So the total fine structure of the atom should be the sum of this one plus the one we had before. And we'll do that on the fourth one and then look at the energy spectra. Okay.